Good evening, everyone. So this is the NPTEL problem solving session for the NPTEL course Introduction to Robotics that is being run for the spring semester, like the odd semester of year 2022. And in this week, you guys have learned about filtering techniques, how we filter out our data, like in our also when we want to do our estimation, how we use these filters to do estimations, uh, more specifically the state estimation we want to do. So in this problem solving session, I will uh, give you guys a derivation of the Kalman filter for a linear system. Okay, and that derivation can be extended very easily to non-linear systems, and that is the EKF, extended Kalman filter, that you guys have studied about. Okay, so let me write the equation of our system. Okay, so last year you guys have studied about, oh, last week, you guys have studied about probability, right, and Bayes theorem. So and Bayes filter. Okay, how does Bayes filter work? So Kalman filter is also, you know, uh, is a Bayes filter based algorithm. Okay, that is BUT, and then okay. So now I'm writing. And what I'm doing is I'm writing the equa- equation of the transition. Okay, of the system. Okay, so last week this was given to you as the transition probability. Okay, and now the transition model has been given to you directly. Okay, that given state t minus 1 and the control ut, what is the next state? Okay, so this transition model has already been given to you, right? And then we say that there is a noise in the process. Okay, we call it the process noise. And I had discussed in the problem solving session last week that where does this process noise comes from? Okay, this essentially, even if your model does not have any inaccuracy, the process noise comes from your control. Okay, because your control cannot be, noise free. Okay, and since we said that the process noise is coming from control, so this ut, we were saying that this was the mean part of the control, and this wt was the noise part. Okay, so now if I only look at wt, I can, okay, this is one more assumption that we take in Kalman filter. All the noise, okay, or all the randomness, or all the variables are assumed to be, or all the random variables are assumed to be of a Gaussian distribution. Okay, so yeah, this is our process noise. Okay, and then comes our measurement model. Okay, and this also last week was given to you in terms of probabilities. Okay, but now you have it directly in terms of equations of, equations of system. Okay, so this is my measurement model. Okay, and how does this work? Okay, so uh, this so this shows me that any measurement that I make, it depends linearly on the state, and it has some noise given by neta t, and neta t again, okay, it is assumed to be a Gaussian noise of zero mean, and let us take uh, p over here. Okay, so this process noise wt, it was a Gaussian noise of zero mean and p variance. Okay, and this neta t is again a Gaussian noise of zero mean and Q variance. Okay, so now what essentially we want to do is we have okay, so we have x hat of t minus 1. Okay, so the mean position or the mean of the states at the last time step, and we have the variance in these positions. Okay, so this p is the process noise or the variance in the control. Q is my measurement noise. Okay, or my noise in the sensor. Okay, and this sigma of t minus 1. Okay, I should write these as pt and qt. The sigma of t or t minus 1 is the measure of uncertainty in the state. Okay, so essentially you can say that x hat and sigma are associated with, okay, are mean and covariance associated with the random variable x. Okay, so now what we want to do is that we have x hat of t minus 1 and sigma of t minus 1. Okay, we want x hat at the next time step and sigma at the next time step. Okay, and over here we are doing, okay, according to the okay, we transit according to the transition model that has been given to us, and then we also include the measurement of it here. Okay, so you can see this is somewhat similar to what we had done in the base filter also. Okay, so now, as always, the first step that we take is prediction. Okay, prediction based on what? Based on the transition model. Okay, so I call the prediction based on only the transition model as x bar t. Okay, so this is the, let us say this is x bar hat. Okay, and so also variance based only on the prediction is sigma bar. Okay, so how do we, like, this is basic probability, but still we'll do it. Okay, if our transition model is given like this b ut plus omega t. Okay, how do we calculate, x hat bar? Okay, basically, how do we calculate the expectation of x of t? Okay, because this is what we want, right? So this x bar hat at t is the expectation of x of t from my transition model. Okay, expectation from x bar t. Okay, so this essentially you can see this is expectation of a x t minus 1 plus b ut plus wt. Okay, since expectation is a linear operator, I can write this as expectation of t minus 1 plus b expectation of ut plus expectation of wt. Now what is expectation? Expectation is just the mean value. Okay, so I can write this as a x hat, right, the mean value at t minus 1 plus, as I told you, right, that ut is already the mean value in my control. Yeah. And all the noise or all the Gaussian part of my control, I have separated it into my wt. Okay, so this goes to yeah, not zero. This directly comes as b ut, and then there is nothing here, right? Because mean, we assume that wt is a variable, random variable with zero mean. Okay, so this is my x bar t. Okay, so okay, I have one of the quantities, intermediate quantities that I was looking for. Okay, now I want what? I want sigma bar t. And how do we calculate the covariance? Okay, so it is calculated as t minus x bar t, xt minus x bar, yeah, x bar t transpose. Cool. So if I just write everything, okay, xt, x bar t from the equations that I have here. Okay, this is my, yeah, so this is my xt and this is my x bar t. Okay, so this is just the expectation of um, write this xt minus 1 minus a x hat t minus 1, and then there should be a plus b ut also, and then a xt. Oh, so but cancels out from both of these terms. Okay, and this is my a x of t minus 1 minus a x hat of t minus 1. Yeah, and this remains, this wt remains. Okay, now if you just multiply everything and open it, let me just write one more step. There is one more thing to take care of. So we can write it like this: t minus 1 minus x hat of t minus 1 plus omega t wt, and then a. Now see, since you have two terms, you can say that this is the first term, this is the second term in each bracket. Okay, so when you multiply them and expand it, okay, you will get four terms, right? And what will be the four terms? One will be just multiplication of the first two terms involving my xt minus ones. Okay, and one term will be only involving my wt's, and the rest two terms will be cross or the covariance terms between my x and my w. Okay, and my w and my x. Okay, so here we have assumed that you know this noise is an independent noise. Okay, basically wt does not depend on x of t minus 1. Okay, because I have told you, right, that this wt, the source of this wt is only my control. Okay, so I can assume that covariance between x and w, it is 0. Okay, so essentially I will be left with only two terms. Okay, this is xt minus 1 minus x hat t minus 1, and then you take the transpose. Okay, this is just linear algebra. I hope that you guys are comfortable with it. And then this is wt transpose. Okay, and then now I can write it like this. Okay, because a is a constant, because I'm assuming the system to be a linear time invariant system. Minus 1 minus. Okay, so now you guys might have started seeing something here, that this term that I'm writing right now, okay, this is the variance at time t minus 1, right? And what is the variance at time t minus 1? I already have it, right? This is just sigma. at t minus 1. Okay, so this term is just sigma at t minus 1 A transpose plus what is now this term, now you can see it is the variance in W. And what was the variance in W? It was P. Okay, so after my prediction step, this is how my covariance changes. Okay, so let me just write both of them together. The my x bar of t, okay, this is my sigma bar of t. My x bar of t is a x hat of minus 1 plus b ut. Okay, this completes my prediction step. Prediction step of what? Of base filter. Because I've told you, right? Carbon filter is derived from the base filter. It is a special kind of base filter that assumes the transition model to be linear and all the noise in the system to be Gaussian. Okay. Uh, Now I come to the second step. Okay. So what is the second step? Second step is the measurement update. Okay. That now I'm saying that I have made some measurement on my, okay, I've done some measurement. Okay, and this measurement I was modeling as what? Modeling as this. This was a measurement model. CXT plus eta t. Okay. So uh, what? So let us say that since I have a predicted value like this, okay, what will be the mean measurement that I expect? Okay. So I'm writing the mean measurement that I expect through this model. Okay. So now again you can do expectations and all, but okay, this will come out as this. Okay, and this neta t. Okay, we had seen that this was a zero. It is a random Gaussian random variable with zero mean and qt variance. Okay, so now if I want to include my measurement, okay, this y hat of t is not my measurement. Okay, this is the estimate of the measurement. Okay, this is just the estimate of measurement. Okay, now what I want to do is I want to include my measurement, or essentially the difference between my measurement and the difference difference in my measurement and the estimate of the measurement, and somehow use it, okay, update my x bar of t further to get the real, okay, or the final, or you can say corrected x hat at t. Okay, essentially the final mean that now has measurement data, okay, or the correction due to measurement in it. Okay, so now for that we need to construct an observer. Okay, and the type of observer that we use in Kalman filter is the Leuenberg observer. Okay, so how does Leuenberg observer work? It is a linear observer. Okay, so I say that my x hat of t is just a combination of my predicted state plus some gain kt times the difference in my measurements. Okay, and difference in my actual measured value and my predicted measurement. Okay, yeah. Okay, so this is the observer that we used in our Kalman filter. Okay, so now what is x of t? Okay, to calculate x hat of t, we need k of t, right? So let me just write it. Okay, let me just replace, this um, y of t and y hat of t with my model. Okay, so this is cx of t plus eta t. Okay, don't forget the noise minus c x bar at t. So if I just write this, okay, so I will write kt as k. Okay, but you have to remember that this k is at a particular time step. Okay, this k will change. T plus kc x of t plus k eta t. Okay. Now, what do we want essentially? Let us assume that you know the actual state is what is x of t. This is the actual state. This is what I'm assuming to be a random variable. Okay, and what is my estimate of this actual state or the estimated state? Okay, estimate is my mean value. Okay, and along with this mean value, I have some variance associated. Okay, so now for this estimate to be good, okay, for estimate to be good, my variance, okay, my variance in the value should be as low as possible, right? Because if my variance is as low as possible or it is minimum, then I can be pretty confident that whatever is my x hat of t is actually a really good estimate of my x of t, okay, or the actual state, right? So essentially, what I want to do is I want the okay sigma of t to be minimum. Okay, but what is sigma of t? Okay, sigma of t is just the okay. If I write it in terms of expectation, it is x of t minus the actual final estimate of t, and then x of t minus x hat of t transpose, right? You can now you see you can call this quantity is the error in x, right? Uh, the difference between the actual value and the predicted value. Okay, so I'll call it x tilde. So what is x tilde of t? It is x of t minus x hat of t. Okay, so essentially, if I write x hat of t from here, okay, it becomes minus kc xt minus I minus kc x, what was it, x bar, okay, x bar of t minus k zeta t. Okay, so if I just write it finally, it will come out to be I minus kc xt minus x bar of t minus k Okay, so for using this, I write my this sigma t. It is my expectation of. Okay, I replace this x tilde here and here. Okay, so what do I get? I get I minus kc x t minus x bar of t minus k neta t, and the same thing but with a transpose now. This. Okay, this is just the definition of covariance that I use. Okay, now if we just expand it, okay, so what do we get? We get, okay, like you expand and multiply, okay, then again you will see, you have to keep in mind here that my neta t is an independent variable. Okay, so the covariance between xt and neta t will be 0. Okay, so yeah, we should write out all the four terms, but I know that when I take the expectation of x tilde, or no, not x tilde, xt minus bar and neta t, okay, and neta t, the covariance, because that is the covariance between x and neta, right? That is 0. So I'm not writing it in the final equation. Okay, so this is my x of t minus x bar t, xt minus x bar t transpose I minus AC transpose. Okay. This is one term, and this is the second term that will be non-zero after we take the expectation. Okay, just remember that. This is my k neta t, neta t transpose k transpose. Okay, so what does this turn out? Kc. This is my expectation of x of t minus x bar of t, and then x of t minus x bar of t transpose with I minus kc transpose plus, now since k, it does not depend, or basically neta does not depend on k, and k is a constant essentially for this random process, so we can take out k, and this then becomes neta t transpose k transpose. Okay, so you see this term here. Okay, this is nothing but my sigma bar of t that I've already calculated. Okay, so essentially my sigma at time t, it is coming out to be I minus kc sigma bar of t I minus kc transpose plus k. Now what is this thing? This is the variance in neta. Okay, and we had assumed that variance in is the neta is what? Qt, right? We had assumed that neta is a random variable with zero mean and Qt variance, right? So now see, you see, this is my final, I can say final variance, but you see there are unknowns. Okay, because I have both the expressions now. Okay, I have my final x hat of t, right? Okay, I have a final x hat of t, and I have my final sigma t. Okay, but you know k is still an unknown. Okay, and we want a value of k that minimizes, right? we want a Kalman gain such that it minimizes my variance. Okay, so that I'm more confident in my prediction or my state estimation. Okay, so how would I minimize my variance? So what does this mean? This means that we want a k for which del of variance over del k is 0, right? This at k equal to k star should be 0. This is the simple trick or the simple result, not a trick, that we have been using since our high school, right? Because if variable is attaining minimum value at a particular value of its dependent variable, okay, or the independent variable on which my final value depends, or the sigma t here depends, then the differentiation should be, or the rate of change of my dependent variable in the direction of that independent variable should be 0. Okay, essentially my d sigma over dk should be 0. Okay, so what I do is I will just expand my expression for sigma t, and then I will differentiate with respect to k. Okay, so what does this come out to be? This is my minus e bar c transpose k transpose minus k c, yeah, slim bar sigma bar, and then plus k c sigma bar c transpose k transpose. What is the last term? K q k q t k transpose. So let me just write everything. Club those quantities that can be clubbed. Okay, this is these two terms are linear in k. Okay, and this term here is quadratic. So this is C transpose plus QT K transpose. Okay, now I do what I just said. Dou sigma T over dou K. Okay, what is that? Okay, this is 0. Okay, 0 minus this will be as it is, sigma bar T C transpose, and here it will be sigma bar at T transpose C transpose. Okay, but you know the variance, okay, here it is a symmetric matrix. Okay, so this sigma bar T transpose is equal to sigma bar. So I'm not writing. Okay, I've replaced already the transpose. What about this? This will be my, okay, this will be K C transpose plus QT, and this is, I'm saying, is equal to, and this, now since it is a quadratic term, so there will be a 2. Okay, like here you can try and do write both the terms, take transpose. Since sigma t q t are variances, their transposes will be equal to themselves. You will see that you will the second term that you get when you differentiate with respect to this k, okay, it will be the same. Okay, that is why I've just written to here. Okay, but when I'm writing to here, I'm essentially assuming that this whole term is symmetric. Okay, and you can check that for yourself. Okay, so if I write it, okay, so 2k c 2k c sigma bar t c transpose plus qt is my, again, 2 times sigma bar t c transpose. Okay, so what is my k final, okay, or the Kalman gain, optimal Kalman gain? T C transpose times R T C transpose plus QT inverse. This is the optimal Kalman gain. Okay, that is, if I choose this value of gain in my Leonberg observer equation, then my variance at the next time step would be minimum. Okay, so now I'll just put this final expression of k in my expression for sigma. Okay, this final expression for sigma, and we'll just get the update rule for sigma, or the final update rule, you can say, for sigma. Okay, so what will it be? I'm writing sigma t is, so sigma bar t will be here, and then minus sigma t c transpose, let us keep it k transpose, minus, yeah, um, kc sigma bar t. Okay, now if I write, replace k here, okay, you will see like this is just small manipulation that I'm doing, that is will make things easier to see. But even if you replace k everywhere, the terms that will cancel out now will still cancel out. Okay, C transpose, and you see this is multiplied by the inverse of the same quantity. Okay, so it will be identity. So it will be left with this only. Okay, and you see this and this is the same but with opposite signs. So these also cancel out. Because this is what I was saying, that even if you put your values of k everywhere, these two terms will still cancel out. But now this is easier to see. Okay, there is a smaller equation. So essentially, the final update rule after sigma, okay, after measurement is, it is, I take sigma bar of t as common. This is my k star, and this is sigma bar. Okay, so this is essentially your, how you do your Kalman filter. Okay, so if I had to just write the steps, okay, you first step was the prediction step. Okay, using what? Using my transition model. Okay, so using that, I had calculated that x bar is a x hat of t minus 1 plus dut. And what was my x hat of sigma bar at time t? That was, okay, that had come out to be a sigma t minus 1 a transpose plus pt. Okay, and what was my second step? Second step was the measurement of rate. So in measurement update, okay, I had calculated my, I know what my optimal K star is. Okay, so I will directly calculate my optimal K star. Okay, I will write it as, what was it? Sigma bar C transpose. Okay, this is all assuming that my model is this. I have a linear transition model with Gaussian noise, and my measurement model is also linear, again with Gaussian noise. So this will be about this we have just derived inverse. Okay, and using this measurement update, I can you know write my final x hat. Okay, so what is the final x hat of t? It is just x bar t plus k, okay, y of t minus c x bar t. Okay, this is your measurement that will come from sensor, and what is your final sigma t? That is just I minus, this is again k star c sigma bar t. Good. So this is your carbon filter algorithm. Okay, these are the essentially the 5 steps or the 5 lines that you write as code whenever you are trying to write the carbon filter. Okay, but what I've told you here above is how we have derived carbon filter. Okay, and now again, if you have non-linear transition models, let us say that you have some smaller here t minus mu t, and again there is noise here, and your yt is g of x of t. So what you do essentially is you linearize these points, okay, or these equations about your previous mean, okay, x hat and x hat at t minus 1 and sigma at t minus 1. Okay, so you linearize these equations. Okay, so let us say that this gives you something called capital F, like equation like this, plus g ut plus some noise, and this yt, when you linearize, okay, it will just give you this is some h of xt. Okay, so what you essentially do is you use in prediction, you use the nonlinear model. Okay, but when you're updating the variances, you use the linearized values. Okay, so basically this will be replaced by your f. Okay, and this here it will be replaced by a linearized, basically the Jacobian capital F. Okay, and again similarly in measurement model here, you will use your this g. Okay, but for everything else, okay, here wherever you are seeing c and all, okay, that c will be replaced by a h, and h is your linearized measurement model. Okay, so when you do these changes, what you end up with is called ekf, extended carbon filter. So I think this will I think you guys understand what I was trying to tell you in this lecture, and I will end this lecture now. Thank you. You can ask any doubts if you that you have. Yeah, thank you. I'll end the lecture.